Welcome to our presentation. In our project, we strive to address a key question surrounding India's sustainability in food production. India, which has a population of over 1.3 billion people, is self-sufficient in its food production. However, its agricultural systems are extremely resource intensive, requiring tons of fertilizers, which are predominantly imported into the country. With soaring fertilizer prices and tight budgets, Indian policymakers have little room for error when budgeting for fertilizers. In particular, they need to offer subsidies to farmers at a consistent and fair rate, and to do so, budgeting for the precise fertilizer amount is key. Rice is the staple food crop for over 50% of the Indian population. Rice cultivation in India primarily happens in the monsoon or rainy season between June to July to October to November. Here, as a team, we attempt to help policymakers by predicting the expected fertilizer input to obtain a desired rice yield.
Let us go into the stages of workflows that led to our predictive model. First, we combined data from iCresat. In fact, we combined several sources of data, and then we refined and centralized it, on which later we produced exploratory data analysis by using various tools built into Python and R. Later, using these tools, we came up to the conclusions that we need to make a clusterization, and on each of the cluster apply regression model that include linear and polynomial regression, support vector machine, and random forests. Based on this model, we built our predictive system that hopefully will make useful suggestions to policymakers for allocation or redistribution of fertilizers. Let me describe the data features that appear in our centralized data set. Roughly speaking, these features can be divided into 5 categories. It's geographical features such as districts or states, its seasonality and temperature, its precipitation, runoff, and evapotranspiration. In one word, is water cycle, its wind speed, its fertilizer input that includes nitrogen, potash, and phosphorus.
Our methodology relies on classifying Indian districts into 6 clusters. This is done using a hierarchical clustering approach, which is validated by k-means clustering. The clustering classification uses similarities in the relevant environmental variables to inform our models. We can visually see the similarities between both clustering methods in the composition of hierarchically defined clusters in terms of the k-means classification. And more importantly, we can visually check the reliability of our clustering on the geographical map of India. Districts that belong to the same cluster will be taken jointly in the regression models for fertilizer consumption against rice yield.
Having grouped districts into clusters, we perform cluster-level modeling. Here is a map of India showing the clusterization generated by a hierarchical classification scheme. Let's start with one cluster, say cluster 1. We take the historical NPK data from these clusters and regress those against the rice yield. So in the plots on the right, you see the fertilizer data on the y-axis regressed against the rice yield on the x-axis. We trial out 3 different models: simple linear regression, just a straight line fit, correcting for the slope; random forest regression, which is prone to overfitting; and thirdly, support vector regression, which handles the outliers really well. We compare the performances of these models utilizing the SMAPE metric, the formula for which is shown on the slide. The SMAPE metric takes values ranging between 0% for a perfect fit and 200% for a null fit. Here and below in the figure, we evaluate the SMAPE metric on our test data for the 3 different models and across all of the clusters. Notice that the support vector regression model marginally outperforms its competitors on all of the clusters, barring cluster 6, where we have fewer samples, only 360 of them. In summary, we have successfully built cluster-level models to predict the expected fertilizer input for a given rice yield. Proposed future model extensions include incorporation of new variables and assessing the impact of off-season farming practices, including crop rotation. Thank you very much for your attention.